Hello, everyone at HelSec, CitySec, and everywhere around the world where you're connected from. And thanks for the nice HelSec community and OSCO in particular, and everybody in the backstage for organizing this smooth streaming. So welcome. My name is Andrei Costin, and I'm a senior lecturer and assistant professor at University of Jyväskylä in central Finland. Moi kaikille. Puhun tosi vähän suomea. So I'll speak English. This is much easier also for our international audience. Today, I am really delighted and honored to be here and to present some of a collage of some research topics going on for years under my supervision and advisory. And today, I really want to focus on insecure firmware and wireless technologies as Achilles heel in cybersecurity or cyber physical systems, because it's important. So yeah, let's get into it. I've already introduced briefly myself. I'm also the CEO and co-founder of Binary.io, which is University of Jyväskylä connected spin-off and deep tech cybersecurity startup, which focuses on firmware analysis and monitoring platform. And that would be great if you could take a look at our web pages and follow us and be part of our success story. Thanks so much to everyone. So this is very short outline of the agenda, what I want to talk today. Again, these topics are not breaking news, and definitely they are interesting and very important, but they are iterating all over. So what we will look today at some IoT or Internet of Things or embedded devices or cyber physical systems, whatever you call them, and their firmware and wireless technologies, and some interesting story about them, especially from the focus of cyber physical systems. So, well, I think it's good to set a common ground. I'm pretty sure everybody knows what IoT is and what industrial IoT is, but essentially these are embedded devices, and these embedded devices, they are everywhere, literally these days. And these devices, they are getting smarter and more complex. And when I say smarter, in the sense they are smarter, but smarter in quotes, meaning that they are not so smart because they are vulnerable many times, but smarter meaning that they get designed and pushed with so much cutting edge technology into them that they are not ready for those technologies, such as APIs, JSON RESTful APIs, XML data processing, sending data back and forth. And all this is fine, but of course, this adds complexity of software, complexity of protocols to everything. And sometimes it just becomes too complex in the general scheme of things. If we also look at these embedded devices, they are getting more also interconnected, that for every device, you literally need a smartphone app or a web application or a web interface to manage them. Then you suddenly think, well, there's a web server and a web application running literally on every device, starting from your router, printer, VoIP phone. And if you've been in cybersecurity and application security quite a while, you know, WebSec keeps giving for several decades. There's like bugs such as XSS, but we cannot get rid of even today. So this is like an endless story when you think about this. So embedded devices are really diverse, and literally everything you use today is one way or another an embedded device, and sometimes the devices themselves contain other embedded devices. And they are so diverse, all of them run some sort of software, many times commonly referred to as firmware. And that is nothing different than normal software, that is just a different terminology, and it has a little bit different type of technology in the back and how it's being written and built, but still it's software that runs on the device. And pretty much your smart TV, even your latest monitors, your smart meters, hard drives, your graphic cards and GPU, and all the chipset on the graphic cards and GPU, they are embedded devices, Matryoshka style, one inside the other, but all these chipsets, they run some sort of a firmware and software. And of course, there's so much interfacing between these chips and then interfacing between these devices that inherently there's going to be problems, and there are actually problems. These examples here are just to show that things that do not look like a computer, they are actually a computer. So your smart TV, your latest monitor, your smart meter, your hard drive in itself is a computer because it has a CPU or a microprocessor which executes some code which is different from your normal operating system, such as Windows, Linux-based operating systems, and Apple-based operating systems. So they run something different, but still they run some code. And that's very important because if they can run some code, this means that there's plenty of opportunity for attackers to execute whatever they want. For example, why not execute a backdoor on the hard drive, something that was done by my PhD colleagues, Jonas Zadak. I recommend to check that work. Or even writing crypto miners that run on your hard drive while your computer runs, or crypto miners that run on smart meters, and everything that can execute code literally. So the main thing here is that embedded devices are ubiquitous, and even if invisible, they are essential to our lives. For example, some of them are pacemakers or insulin pumps, neurological implants. They can operate for many years, and they might not receive no security update or no software update whatsoever. So if there are bugs, they are there for quite some long time. And this usually goes into critical infrastructure type of things that might be a couple of meters below the ground, buried in the critical infrastructure stuff. And you cannot just go and take it off and update the software whenever you like it, like we do in very agile DevOps, DevSecOps thing for the web apps. So they require a little bit different approach to cybersecurity and to how the bugs are being fixed related to security or functional bugs. And of course, they are having a large, and I would say actually a growing attack surface, because besides the networking services, and web interfaces and forgotten debug interfaces on the device, they keep piling a lot of different, as I mentioned, smart or RESTful APIs that enable feature-rich applications and interconnection of those devices to the cloud, to MQTT, to monitoring, dashboards, analytics, and whatever not. And everybody tries to come up with their own innovative solution, and many times homemade protocols are not necessarily the best or the most secure, especially if they are cooked in a hurry. So we keep seeing a lot of this protocol, or let's say industry or device-specific protocols that basically make the same mistake as the code in the 90s. It's like there's a running joke, but the security of embedded and IoT is more or less like the 90s of web application security. So, I mean, you just poke it around and suddenly you've got a 0 day. So no problem there. So there are a number of challenges when we think about analyzing these devices. First of all, which is not necessarily mentioned here, is that they run many times code that we are not, as a security researchers, we are not necessarily super familiar with. For example, if you know assembly x86, 86, 64 bits by heart, that is nice, and you can own any laptop server via proof of concept. But then if they run some very obscure hardware architecture, running softcore or hardware-based CPU core that is not known. And when I say not known, is something which is completely different than our MIPS PowerPC. There are so many other architectures that we don't know. And getting low level into that kind of stuff is difficult. But then there's also a large number of devices and a heterogeneous number of devices. And to be able to actually do this analysis fast and quickly, it is preferable to have options to analyze the vulnerabilities and the security without the devices themselves. And there's also some other aspects to that, but some of these devices are impossible to get. For example, if you want to pen test a Tesla, well, you need to buy a Tesla, right? Nobody will give you a Tesla just to pen test. So it's quite expensive, sometimes prohibitively expensive. Some other type of devices, for example, if you have the money, but you want to pen test a fighter jet, most likely you will not be able to buy the fighter jet because of the regulatory thing. You might be able to get the firmware or the code, but which is also hard, but the fighter jet most likely you'll not be able to get. So there are many obstacles with some certain types of devices to get, and that's why many times it's good just look at the code, because usually it's where the main security problem lies. It's in the code most of the time, like 70 to 90%. It's application or software related code. Hardware related bugs, they are there, but they are harder to exploit. Or they go through so much verification and validation that literally the number of hardware bugs are quite limited. Then there's a large number of firmware files that you need to look at, and you need like a scalable architecture to do this. And that is like a side note. This is what we actually do at Binare. And then you need generic techniques, because yeah, it's nice to find a bug in one system, but then if you find just in that system from hundreds of thousands of devices or firmware, and you cannot apply the same technique to other findings, then your technique is basically like a one-use tool. Imagine you have a screwdriver and you can screw just one type of screws with it. So you would need millions of screwdrivers, how to be actually effective in your houseworks. So this doesn't work well. And normally, if you have a technique like a screwdriver, it needs to be quite versatile in some ways. So it applies to more heterogeneous systems, devices, and firmware. Then it's also, there are some other challenges that I'm not going to go into detail, but basically they're increasingly smart and connected. So usually the main focus is on web interfaces and APIs. This is like the usual low-hanging fruit, but there are so many other protocols that require more deeper understanding or more reverse engineering abilities and so on and so forth. Okay, so that's kind of setting the stage from my perspective about the challenges related to firmware things and the different types of devices. And I'm quite sure in the audience, everyone has heard about IoT devices. They've done their hands-on penetration testing or security assessment of some IoT device. Maybe it's a Raspberry Pi, maybe it is an Arduino, or an Espressif 8266 or Espressif 32, or a gazillion of other hardware options that are available, and also at affordable prices and open source firmware and so on and so forth. But I want to focus on some motivating examples that I've been working on, and they are not necessarily based on let's say the usual Raspberry Pi type of scenarios. And again, Raspberry Pi, as a small parenthesis, is a very good learning and sharing tool. It is also ARM-based, but makes it relevant to many applications such as smartphones. Whatever we have today on the market most likely run some sort of a ARM processor or ARM core. So the security analysis for ARM is very relevant and very easy to transfer from Raspberry Pi to other types of devices. But Raspberry Pi, let's say, is usually a proof of concept, and normally you would not find them in critical or in cyber physical systems. For example, I haven't heard about any airplane running on Raspberry Pis, right? Because they need to have some sort of hardware guarantees and firmware guarantees, and there are so many other standards that they need to implement. But there are specialized avionics devices that we will get into in a couple of minutes of my talk. But one example I like in particular is this wireless firing system. Why? Well, first of all, what is a wireless firing system? It's a system that wirelessly fires something. Usually it's a projectile for a fireworks display, but this system can also are also used for military and police exercises. For example, if they need to remotely fire some projectile when they do their scheduled exercises or maneuvers. Of course, it's not so common that they use necessarily wireline firing system involves military exercises, but it's very relevant, and the vendors actually advertise these wireless firing systems also for tactical and military application and trainings. But most common, they are used for fireworks display. So how it looks, normally this is how they look in the sky, but in reality, in the backstage, what you don't see when you look at these fireworks, and I hope after this talk you'll look with different eyes at the fireworks whenever you see them, at least I'm doing so, I'm looking them with totally different eyes. So what you see in the sky is totally different from what is in the background. So in the background, actually, there are a lot of tubes that are called mortars. They're pretty much very thick, resistant, sturdy pipes, which host the display shells. Basically, it's let's say a chemical component, explosive, combined with other chemical things that get ignited, and they become a projectile that go into the air, and then they provide these nice visuals on the sky. But these are pretty low tech. There's nothing particular about these mortars and display shells, meaning that the mortars are just pipes, and the display shells, they are of course sensitive chemicals and they need special handling, but again, it's just chemistry that is known for thousands of years from let's say Chinese celebrations with fireworks thousands of years ago. So it's not necessarily IoT related, at least these layers. But what goes next is it starts becoming interesting, because we are talking about wireless, right? So the idea is that these mortars, they need to be ignited. Well, the display shells need to be ignited. So there is a igniter fuse clips, which is kind of two wires with a clip like that. And these two wires, they are usually connected to some power of some source of high amperage. That at a particular stage, this fuse has basically burns. You know what a fuse means, and when so much or exceeding current goes through the fuse, there's a very tiny wire. Maybe it's hard to see here, but if you find the picture, you can zoom it. It basically becomes like a flame, and it is enough to ignite the display shells, but then they come into action as explosive. So the whole idea of this igniter fuse, that they start pumping some current through them, and it burns the fuse, which creates kind of a electric match. Okay, so there's not somebody putting the match there, but they're doing this electrically. And now the interesting part comes is that usually these igniter clips, they are connected to what is called a firing module, which is a box like that, and it has like it depends on how big the fireworks display must be and how big the show must be. It contains between 8 to up to hundreds of these connectors, where you can connect literally hundreds of igniter clips. So one clip goes into one of these red slots, and one clip is connected to one of these mortar tube. So what happens is then when this firing module gets a command to fire a particular tube, it will just activate the current through the particular pin, and it will fire the display shell. Now, this thing is completely electronic, as you can see, and it has also the buttons that you can be operated locally. It also has some kind of a safety key, which is in some attacks they are not effective, at least from what we have found. And it has buttons for local programming, but then the interesting part comes that there's usually it's this one is very close to these mortar tubes. So normally these firing modules, maybe it's about a couple of meters from the firing mortars. And what it means, it would be like really dangerous to be there, an operator to be there and manually operate this firing module. Therefore, this firing module has a wireless communication, which goes up to 2 kilometers in some cases. In many cases, it's a Zigbee, but sometimes it's a normal ISM band custom radio frequency protocol, which is easy to sniff and replay. But even with Zigbee, we'll see some funny stuff. So these firing modules, they they are connected through wireless communication through a remote control module, which is somewhere on a safe distance from these firing monsters, so to speak. So everything must be safe, and normally there's some operator desk, like fireworks designer or fireworks operator, who is sitting somewhere in the dark, far away from these mortars, maybe 500 meters. Sometimes they are on a ship, on a sea, because sometimes they put this firing from the floating platform on the sea. And they operate this firing module. So basically, this firing module is the main thing, which is also an electronic device, and it has a CPU, and it communicates wirelessly with this firing module and activates different mortars at different times. So these mortars can have different displays, colors, and they can be configured in such a way that they are choreographed. There's a term that they make fireworks choreography. There is software that can be designed and employed to actually, it will tell you in which mortars you have to put what kind of shell to look, to perform a particular visual show. And then it will also generate the program that you can put on remote control or firing modules. And that program can be a CSV file. And again, if you know, parsing CSV files can also be funky, and sometimes it goes buffer overflow, but that's another story. So this CSV file basically can program the entire thing to do things automatically, but of course the operator can punch the buttons here so that they have more manual control and take over from the programmed output. Now, this is how a wireless firing system looks like in 10 minutes and how it works. If you didn't know how the modern fireworks work, now you know. But we are not here to talk about fireworks. Of course, we are talking here about wireless communication and cybersecurity and how it relates. So let's look at, well, is there any way that the attacker, so when I found these modules, I say, hey, okay, how do they work? And clearly there's no electronics here, there's no smart things there, but definitely here and here in firing modules and remote control modules, there might be some smart things. And is there any way an attacker can, you know, remotely trigger the thing without the operator knowledge or without operator authorization? And that would be like really dangerous. If you have a crowd and a very big show, first of all, it can be like, you know, disappointing if the show doesn't go as planned, but it can also be dangerous, which is more important than the show itself. And there are actually cases when these fireworks went really, really bad with harm to the people. And that's the main thing. But these are cyber physical systems that if something happens in the cyber domain, meaning the firing modules and remote control and wireless communication in between, it immediately have effect on the physical domain. It means some injury, it means some immediate danger to people using or being around this system. So cyber physical systems are some very special type of IoT device because it must be understood that, you know, if you have a sensor in your home, it's a cyber physical system also, but it's in a way is not acting on the environment many times. Most of the times it just senses some kind of temperature, humidity, and it transfers it to a nice dashboard. So it doesn't, it has almost zero chance to make harm or damage to you or your apartment. However, when we are talking about real cyber physical systems, such as these wireless firing systems and avionics will look, or maybe some energy and nuclear plant operating embedded devices, those are putting real danger on the environment around them. Okay, so we said, okay, let's look what's inside this. We started actually from firmware. It was funny because, okay, it was the device. And we said, okay, the device is quite expensive. It was close to €1,000. And we say, okay, before buying the €1,000 device, maybe let's try to see if it contains something juicy, first of all, just to know if it's a good money and time investment. And then we started from the firmware, which was available, and that's normal that it is available. That should be not a problem for the firmware to be available, as long as the firmware is secure. There is no worry. I mean, it doesn't mean that the vendors needs to start pulling their firmware off the internet. It means that it means that the devices will not get their updates, which is really bad. So they need to put their firmware on the internet, but they need to develop the firmware in a secure way. That's the main message. So we started the firmware, we performed the unpacked, there was no encryption, so there was not necessarily particularly hard time to do this. Of course, at first it looks like that, and that if you are not familiar with embedded programming, then it can be a little bit puzzling. But then if you perform some embedded microcontroller type of programming before, you know it's iHex format, and basically it's a Intel hex, or it's basically a way to encode the bytes into their hexadecimal representation, and have also the offset of the memory address where these particular bytes should be written when the firmware update performs. We analyzed it, detected the CPU. It is a Motorola M68K based CPU. So this Motorola is quite well known. It has, if I'm not mistaken, they were some Debian Linux ports that worked on Motorola 68K. In fact, it was a Motorola 68K base CPU, but it was a Freescale Fire something. Anyway, we looked through the firmware, found UART consoles, debug interfaces, found boot prompts and Zigbee functions. Say, okay, well, let's look really interesting, because it seems like when you see on the internet to buy the device, it looks like this, but you don't know what's inside. After looking at the firmware, and we see, well, it has a UART port, it has a console, we can connect our UART thing there and get a boot prompt, and also it has Zigbee. Then, of course, it sounds like really good. So the decision was immediate. Okay, we buy the device. So it was, in fact, my own personal money. So again, that's another message I want to say. If you want to do real research, you have sometimes to bet your own money. If you really want to do an impactful research, it's good if you can. Of course, some things are prohibitively expensive. So sometimes grouping together can help. But again, many times, if you expect that the devices will be just available like that, it's I would rather disappoint you that you need to somehow think how you can get really impactful devices, because everybody has a Raspberry Pi and there's not much like unknown there to explore, so to speak. We buy the device, we set up it, and then we disassemble also the physical device, connect UART ports, analyze it further. So this is how the device looks like. This is the main remote control, and this is the firing module. They're slightly different, but the main thing is that they both contain the Zigbee modules that they communicate. So it's a mesh connect Zigbee-based module. They have a main MCU, which is, as I mentioned, it's a Motorola M68K based. There, the key switch, like a physical disconnect of the power if something goes wrong, so you cannot properly operate or fire the thing. But then interesting part is that it has the JTAGs and UART and USB port. So there's plenty of hardware and debug interfaces that we can play with. So that was quite interesting. The same on the firing module. You can see here the very common, it's even written COM, so it's communication serial, UART port. So a lot of places to start playing, finding vulnerabilities. We didn't even try very hard, so to speak. Of course, there was quite some effort in reversing and analyzing, but what I mean, we didn't have to, write crazy type of exploits for Motorola 68K and do crazy stuff, because some of the things were quite obvious. So we started. We say, okay, why we don't want to do really complicated stuff? Let's say, start with the simple. Again, the recommendation is when you have a complex system, try to look for the weakest link. And usually the weakest link is the wireless communication, because it's pretty hard to get it right. And even if it's using the latest communication protocols, even the configuration and setting up the keys can also be a problem. Sometimes the keys, let's say if it's a WPA free, sometimes the keys are just hard coded in the firmware, and when you don't need to run crazy air crack ng or whatever you need to run, because you can just take the key because it's hard coded, right? So sometimes the simplest approaches work. That's another point I want to make. So we look at the ZigBee protocol. We also have this Snap, which is the vendor of the ZigBee modules present here. This is kind of a programmer. What it means, it means that it has a ZigBee inside, a ZigBee communication, and it can remotely, wirelessly program the firmware, not of the devices, like not the main CPU, but the firmware of the ZigBee communication modules, which is another thing that you can actually, let's say, backdoor the ZigBee module itself to receive like a special knock command. But we didn't made this firmware ZigBee modification. We were analyzing just the ZigBee protocol. There were a couple of other devices that we've used that are open source and integratable with open source software such as Killer Bee firmware, and they work nice because they can allow sniffing mode on the ZigBee. Basically, we use this Snap SS200, which is by default. It's a closed source proprietary, counts some Windows program to analyze the packets. And then we also use Econotag, basically the injector that would inject the packets that we want. So what we did first, we analyzed the communication using the Snap device. Like we were playing like the normal operator, punching the acknowledge ARM button. And the important thing is that because it's a mesh network, there's a lot of ping and ping replies from the devices, like the firing modules and the main remote control. And then at some point, the remote control sends this interesting packet, which is acknowledge ARM. So basically, the main remote control sends a command to the firing module. Okay, you should arm now, and the next time I press a button, you should actually ignite the mortars. And then the firing modules replies back with acknowledge arm. So it says that yes, I am acknowledging the arm, and I am ready to fire. And these are pretty normal terminology in this explosive type of communication. So arm device, disarm device, acknowledge arm, cancel arm, and so on. And we captured these packets, and that's important to see this 04 for the 8A. It's the time of the packet. You can see that it's a multicast RPC, so everybody in the network, in that mesh network, can see. And when we sniff it with good fat on the Econotag, then we can see the same packet 04 for the 8A, which is basically firing the thing. So basically, this is there's a video, but well, video is quite old and not so high quality and not so interesting anyway. It's just a flink, but you need to see it live to get a better taste of it. But the bottom line is that we have been able, just by looking at the firmware when acquiring the device, intercepting the ZigBee packets, even though the ZigBee itself has option for AES encryption. It was not used or activated, so they were using more or less plain ZigBee communication and without any digital signature nor encryption. So we were able to inject, capture, replay packets, and we've been able to remotely trigger the firing modules. So in real life, if somebody is sniffing the traffic near a fireworks display, they could replay it in the immediate seconds, and then it could be really dangerous. So we've informed the vendor. They acknowledge us. Well, it was done during my PhD at Euricom. Well, they were a lot of back and forth. The bottom line here is that, unfortunately, some vendors, not this one, but some dealers would use or are interested to use different tactics, you know, to, let's say, gain unethical competitive advantages. So sometimes they would even employ this kind of exploits against competitors to show that their devices are insecure and bring damage. So it's a very, very complicated type of business and a lot of danger. But anyway, we've handled it as a responsible disclosure, and it was a really interesting project to see. Again, firmware, wireless communication, two things that were like the weakest link in the device, which is an important cyber physical system. So if you're interested in all the gritty nitty details, you can check our paper here. So, and some other, let's say, dangerous items such as Linux powered rifles hacking and smart gun hacking. So these devices getting smarter but dumber at the same time, and it's really a dangerous mix of technology and cyber physical systems. So that was like the first thing. I think there's maybe 15 more minutes. I try to also be on time with that, but yes, the other type of physical system are the airplanes and avionics. So the airplanes, including its avionics, is basically a cyber physical system. It's an airplane that can take automatic, let's say, decisions sometimes. It flies on autopilot and is driven by fly-by-wire avionics type of system. So most of the time, or many times, if I'm not mistaken, the pilot is just overseeing the operation of aircraft. I mean, of course, it controls a lot, but many times it flies on some sort of autopilot, and all the things are made electronically. So there's a lot of data buses, ARINC data buses, and so on. But the idea is that these networks inside an airplane, they are quite complex, and they have many input and output interfaces. Like if you start thinking about it, all the in-flight entertainment which goes into the cabin, then there's a lot of communication radios between the pilots and the ground stations. There's the incoming and outgoing satellite communications to the airplane for GPS or data communication, and so many other protocols in between. So there's quite some complexity in the whole, let's say, next generation aircraft systems, and how they communicate between themselves, how they communicate with the satellite, how they communicate with the ground stations, and so on. But the idea is that there is a protocol which is called ADS-B. It's automatic dependable surveillance system broadcast. So it's kind of a very sophisticated name for a system that provides broadcast and receiving of traffic information from airplanes or other ground objects such as cars on tarmac, or for example ground station towers. And this is used in particular for increasing the visibility or the accuracy of the traffic display on the air traffic controller towers, and also to optimize the flight space and the distance between aircraft. It just gives more precision because it's GPS based. So in the, let's say, old technology, it used to be what is called the primary scanning radar and secondary scanning radar, or PSR, SSR. They are basically those rotating antenna that would beam an energy into the sky, and if it receives a bounce back, it knows there's an object, but it doesn't know what exactly is there. This ADS-B is more like digital, but the airplanes actually encode a lot of digital information about its identity, about its flight number, and let's say unique identifiable registration number, what is called ICAO 24. Anyway, there a lot of terminology. I don't want to spend a lot of time on the terminology because I invite you to check the papers that we wrote. But there's basically two types of things: ADS-B in and ADS-B out. ADS-B in is basically an aircraft or a system receiving ADS-B traffic and displaying it on the cockpit to the pilot. And ADS-B out is actually the aircraft or ground vehicle sending data to other ADS-B in capable devices. So most of the times the devices should support at least ADS-B out, because the idea of the next gen is that all the vehicles at least should notify all the other vehicles that they are there. And the main thing is that at least the air traffic controllers and all the towers, they have the ADS-B in capability. long-range ADS-B in capability. So they see all the vehicles that are flying or moving on the ground in their area of responsibility. Of course, ideally is that also all the aircrafts must have ADS-B in, and that will also help the pilots to have better visibility of the airspace around them, avoid collision, or take a more informed decision when doing some maneuver, or get a better communication with other aircrafts. And basically, most of the, let's say, big or serious aircrafts, they have ADS-B in capability. The smaller ones, or let's say the general aviation, the ones that are operated by amateur licensed pilots, they might not have necessarily ADS-B, but there are some technologies that allows this to be integrated cheaply these days, and I'll show some example. Most likely you have used this Flight Radar 24, and if you didn't know until now, basically it's how this website works. It's based on crowdsourcing from the community. So there's a crowdsourced community throughout the world that have some ADS-B in receiver, and then they source all the data to Flight Radar 24 or similar types of servers. And then they aggregate all the data, correlate, clean it up, and then display on the maps. So there is no actual magic how it works. And most of the aircrafts, they must do ADS-B out because this is the mandate. Now, okay, then 2012, when this system started to be more or less developed, or because it started to be mandated from 2020 or 2020 in US and 2021 in Europe, but its development and implementation and integration started about 2010. And then in 2012, these ADS-B receivers started popping up on the market, and it was something, again, similar to the fireworks. I said, okay, that looks like a really interesting type of device. Let's look how it works and how it can be basically attacked. So, well, back at that time, I think the cheapest one was a couple hundreds of euros, and the most expensive ones were maybe up to 2,000. So I think, if I'm not mistaken, the Kinetic SBS, they were about $1,500 to $2,000 US, and it was just a receiver. But anyway, there were, of course, other smaller one, micro ADS-B type of things, and micro ADS-B USB that were like more budget versions of ADS-B in receivers. So, okay, I bought couple of these devices again. Self-investment to say, okay, let's see what this, again, this is very important, because if you really want to do research on something important, is really important to look at something different that nobody else is looking, or maybe it's a little bit more expensive than something else. So at least you have something different than whatever other people are studying. Well, this is more like a technical stuff. I don't necessarily need to go into that, but there are two frequencies, 1090 megahertz and 978 megahertz. 1090 is more like international, and 978 is more or less in North America. But 1090 also works in North America. So they are called slightly different because they have a little bit different modulation and packet formats. So MODES is the simplest one, but it doesn't have like a lot of, let's say, the length of the packets are a bit shorter, so information there is not so rich as in UAT, but still both of them, they are actively used for ADS-B in and out. This is the modulation format for 1090 MODES, and it's called pulse position modulation. It's quite simple, but again, 1 bit is 1 microsecond. Quite simple, not much here. There are two types of packets or data blocks, 56 bits and 112 bits. And regardless of the type of the block, it must contain a mandatory ICAO address, which is a 24-bit unique identifiable registration number of the airplane. It's not the flight number, it's actually the registration number of the airplane. So you can think of it as a registration number of a car, or the registration number or your MAC address of a network card. So this is kind of something equivalent for the ADSB transponder. Okay, well, it's called transponder, transceiver if it can transmit and receive, transponder if it can only transmit. So what we have found back then is that basically we didn't have to do a lot. We've implemented very simple. Basically, we've implemented the protocol itself, and reading the specs, it was very clear that there is no message authentication and entity authentication. So basically, everybody can just tune in to 1090. And again, please don't do this because it's unauthorized. You need a license for that. But it's really nothing prevents an attacker, a well-motivated attacker, to start transmitting on 1090 fake aircraft packets. And there have been cases, and basically there is no entity and message authentication, and it's a completely clear text broadcast type of a system, and that's kind of a cybersecurity nightmare. Basically, it doesn't also offer a temporary identifier, so there's no privacy. So if you have you are a billionaire or a millionaire or just have a private jet, and your private jet is registered in some open access registry by default, then everybody can track where you have been going, because your airplane would squawk or transmit that ICAO 24 identifier. And this is actually how they track some of these, let's say, Hollywood stars or prominent figures, because they fly their known private jets, and paparazzi just look at this registry of known star private jet numbers, and they look where they are. Are they going to Cannes? Are they going to Los Angeles and things like that? So there's no privacy. Of course, there's also no message integrity, because whatever is in the packet, there's no there's some checksum, but again, it's a error checksum, is not a cybersecurity related message integrity, and it can also be replayed. All the messages can be captured and replayed, so there is no freshness. So there's a lot of like fails from cyber perspective, from cybersecurity perspective. When you implement a protocol, all these shouldn't be like that if you are taking a secure by design approach. Clearly, it's an insecure by design approach when this protocol has been designed. And the problem is it's a multi-billion implementation already, and all the aircrafts have these, let's say, insecure devices, and most likely they will stay there for the next 10, 20 years, because they are already implemented, and companies will most likely not invest another billion to secure them. And there's also not an easy fix. Even if you really want to add cryptographic keys, the length of the message, like 56 bits or 112 bits, doesn't allow of a lot of cryptography going on there. If you have to transmit a 4096-bit RSA key, then it will take a lot of packets just to exchange the keys, right? So it's a kind of a problematic situation. Anyway, there's been also examples of abuse of the system by licensed pilots. So pilots setting their flight numbers to whatever they want. So you can see that there like a lot of weird thing going in these ADSB packets. Of course, it's kind of not according to procedure, but there is no technical thing that can prevent such identifiers to be put in the packets. Even for licensed pilots, again, these are not like prank. These are pilots who are flying real pilots, and they can set up the transponder to contain some data, and they choose to set this. Of course, there is also the Air Force One squawking its two of its known addresses here and there. So it's again, I think it's a matter of national security if somebody can automatically track with some auto-guided vehicle this ICAO when it's really dangerous for certain countries, so to speak. Again, we've implemented the attack. Well, can I go 5 more minutes? I hope. Is it okay? I was told that it's okay, but again, please feel free to stop me if it's too much. We've implemented using the attacks using software-defined radios. Again, it required some investment. Now the software-defined radios are much more accessible. You can buy, let's say, a very good versatile one for maybe 150 euros. I would not advertise any particular one. There's a lot of options out there, so feel free to ping me if you don't know what to choose, but we can do this in private. There's also a lot of other security, biosecurity type of protocols in military, ADSB, which is mode 4, mode 5, but we didn't even take a look at that yet. So if somebody in the audience has some of these devices to donate to us, we would gladly receive it and reverse engineer it for cybersecurity of those users using this type of devices, very specialized type of users. Specs are available, but the devices are prohibitively expensive or are impossible to get without special license, of course. But again, we use the responsible disclosure about this ADSB, and somehow there are some fixes, but too little too late, so to speak. Because, well, not much has been made since then, even though there is a cybersecurity for civil aviation established by ICAO, and this is also thanks to some of our works in 2012. So that's good that they acknowledge their researchers, but unfortunately, it's like a very slow moving process. So 10 years later, that's something very, very fresh. It's basically fresh from the oven, what I'm showing here. Again, some things are under review, so I cannot disclose a lot of information, but basically we looked at even more details because, as I mentioned, all these avionics devices, they are embedded devices in cyber physical system, and they run firmware and software. So they process some data by the firmware and software and process the protocols. And there's, as I mentioned, ADSB or GDL19, and they are unauthenticated, unencrypted, wireless broadcasts. So usually this is the type of things that make every cybersecurity researcher scream. So I think this picture basically depicts what's going on in the head when you see this. And most importantly, is connected to autopilot. So if you look the diagram, I didn't put it here, but if you look diagram of this autopilot, then it has ADSB in and GDL90 in, and then the output goes to autopilot controls. And if something goes bad in ADSB, so there's slight chances that it could interfere with the autopiloting features. At least this is my feeling. But I'll show you a very quick demo, and it's a denial of service demo. Basically, it's a remote denial of service. So imagine you have an airplane, if it's a private airplane, or it can be a commercial airplane, that has this screen about what airplanes are above, and you're flying about 400, 500, 800 kilometers per hour, and then the screen suddenly crashes. It's like not the most pleasant experience, especially if you're running nighttime or during a storm or low visibility situation. And denial of service might be okay for social networks. I mean, okay, it will be back in a couple of times, but it can be really catastrophic for safety critical systems. So yeah, let me go quickly and show this. So this is basically a mobile phone, a smartphone with what is called electronic flight bag. It's kind of an application that is installed on iPads or Android tablets or smartphones by, let's say, pilots. They are usually installed on by the private jet pilots, but it can also be installed on commercial air jets. And they use this to have ADSB in functionality without investing like hundreds of thousands of euro, which they normally would do. So there's a small device which costs a couple of hundreds of euros that receives ADSB in, and then it connects via Wi-Fi. It creates a Wi-Fi hotspot, and the smartphone acts just as a screen for the traffic. So we are able actually to remotely inject special ADSB traffic so that we can remotely crash any ADSB in device. Okay, so what you see is basically is a screen that the pilot would see, and then it will just crash in less than 30 seconds. So now it's basically going through the hang mode. And yeah, so this is kind of, it maybe doesn't look very, let's say, suggestive, but what I'm trying to say is that we are able to do this remotely, and this type of ADSB traffic goes into 98% of all the airplanes. So I'm quite sure there are some airplanes that are vulnerable to this type of denial of service attack, and we can keep doing, like an attacker can keep doing this like on a continuous basis. So it will be a complete unusable cockpit, so to speak, at least from ADSB perspective, not other perspectives. But yeah, so we demonstrate this denial of service, and what we are working in progress. If you read this RCE or remote code execution, and normally the denial of service and crashes and remote code executions are quite well related because of the memory problems, and I think we are getting close to that. So that's work in progress, and if we can do this RCE, then it's a entire system takeover or subsystem takeover, and that's even more dangerous. Well, the team in this project that I've showed you, it's quite extensive. We've spent more than 1 year developing these new attacks. Hannu Turtiainen, Syed come here especially. These are the papers that I recommend to check. So the one from 2012 and these 3 ones that are upcoming. And I said, as I mentioned, they are under review. So all these 3 are related to these new novel attacks that are denial of service and other type of attacks on ADSB. So we are going one step, not just spoofing the targets, but we actually remotely attacking the devices that are supposed to process ADSB data and do denial of service and remote code execution, which is like really mind-blowing, because again, it's a non-secured communication channel broadcast, and it's like really, really dangerous. Some more reading material, but I think I'm over the time. Before I stop, the summary is basically critical infrastructure and cyber physical systems. They run heavily on embedded, and cyber physical systems. They are very important to many aspects of life. But unfortunately, IoT, industrial IoT, CPS, embedded are so vulnerable that there's so much things to be done by the community, by the vendors, by everyone involved. And final thing, as I kept mentioning, invest in your own research. It costs, certainly at the point when you invest it, but it pays off in the long run, but you learn and also you uncover new things. So this is how I reached at least these 2 types of research. Was like a huge investment, but it pays off really well in the understanding of cybersecurity. Some shameless plug, please welcome to attend our webinar. If you're interested more in firmware analysis, welcome to everybody to this webinar. And I thank you everyone again for organizing this. And if there's any question, or you can ask now, and thanks for HelSec crew to deliver the questions, or you can reach out to me at these email addresses. Thank you so much again.
Thank you, Andrei. We do have some questions indeed. And also, hi stream. I am actually Tatu, or Digital TA. I'm from HelSec. I'm one of the founding members there. Osku asked me to help him since he doesn't want to do both the questions and the stream stuff. But yes, so first question actually is mine, is that the similar systems as the wired demolition one shown on the presentation are also used in demolition, like for buildings, quarries. While researching it, did you come across any that would be wireless used there? I know in quarries you need to put it pretty deep in the rock, but in buildings?
Yes. Actually, that's a good question. Basically these wireless firing systems, they're also marketed, from what I have seen, they are also marketed for demolition.
Yes.
I'm not sure for industrial deep ground, but certainly for building demolition, because these firing modules, again, this igniter clips can be 10 centimeters long, but it can be also up to 1 meter long. So it's good enough. And even if this firing modules is destroyed, is anyway cheap compared to the entire operation of demolition. But yes, they are used. I don't know, I don't have like a percentage how much more popular they are compared to the wired ones. They definitely make the operation less expensive because there's less kilometers of wasted cable going around. And but yeah, it's happening. Yes.
Okay, good. Second one. So next one was from Bogdan M, and he asked, "Hi Andrei. So how much money do you spend on buying devices at HelSec per year?" I guess.
Yeah. Basically, you don't want to hear this number, but to be transparent and honest, definitely it goes good couple of hundreds, sometimes 1,000-2,000 of phone, because sometimes these devices cost expensive, and I really am interested into that. So that's my own money. But again, it's like sometimes there's a year that I don't buy anything, but definitely if you really want to study stuff, you have to invest, and sometimes nobody will buy these devices for you, even if you work for a very nice organization or company. They'll say, well, it's not the main thing for us, so you have to do it on your own, right?
Yeah, luckily some hackathons and bug bounties exist, so maybe.
Yes.
All right. The next one, actually, Cyberben asked two questions which are quite connected, so I'll just say them both. So, is ADS-B used as a trusted source for information for flight maneuvers, for collision avoidance and such?
It's a good question. I think, well, definitely it's taken as a decision making mechanism by pilots in low visibility, and also by the traffic controllers when there is no other source of communication. For example, the VHS voice goes down. For traffic collision avoidance system, TCAS or TCAS2, actually there's a slightly more complicated system, but it still works on that 1090 and 1030 megahertz frequency. So somehow it overlaps with ADS-B, just has a different protocol. And definitely there are attacks on TCAS as well, because it's the same unsecured, clear text, non-authenticated, no digital signature type of message exchange.
Yeah, to my best knowledge, an autopilot will not change the heading or altitude of the aircraft based on outside data because of these issues. But this is not 100% confirmed, which is what the next question was. What would a real plane do when the system sees a few planes in front of it, and at least one on a collision course like the demo, but more targeted?
Yes. Again, I'm also definitely not a pilot, and haven't never used like real aircraft cockpit, so I would not be able to tell from this operational perspective what happens, and what the pilot should do. I think a licensed pilot would explain better, or somebody from air traffic controller organizations. But definitely from cybersecurity perspective, I think it raises quite some concerns. And I think spoofing is okay. It can be overcome operationally by the pilot. My concern is more about denial of service and remote code execution, which is like completely remote, and that's worse. The pilot cannot do anything there. So I think that's, of course, they are not connected to the autopilot, but then if there's a remote code execution, there are so many avionics bus architectures that anything is possible.
Indeed. Okay, that was the last question that we had there. Of course, please do come on the Discord, and I'm sure someone might have even more there. And yeah, there's the webinar. Everyone attend that. Thank you very much. We'll go on a short break, and after that we have the second speaker, Osku. What was the talk for that?
Thank you so much.
Thank you.